Okay friends, welcome back. Again we are going to discuss about Lna design. So what is Lna design? The first stage of receiver is low noise amplifier whose main function is to provide enough gain to overcome noise of subsequent stages. Provides this gain while adding as little noise as possible. It must have minimum noise figure. It must produce large signal without distortion with constant input impedance, usually 50 ohms. Minimum noise figure from optimum sources impedance can be defined by four noise parameters GC, BC, GU, RN. GC is equal to correlation admittance, BC is equal to correlative susceptance, GU is equal to uncorrelated admittance, RN is equal to noise signal resistance. To develop a design strategy that balances gain, input impedance, noise figure and power consumption, design narrowband LNAs with near minimum noise figure along with an excellent impedances match and good power gain, all within a power budget that is specified. It should have large gain, no noise figure, large bandwidth, linearity and proper impedance matching. Next one, the mean square drain current noise and gate current noise equations are I square Nd is equal to 4 kT gamma G D naught into delta F. I square of Ng is equal to 4 kT rho Gg into delta F. Gg is equal to so wait, Gg is equal to omega square C square Gs by pi G. Correlation coefficient formally defined as C is equal to Ing into Ind by square root of I square Ng into I square Nd. The mean square drain current noise and gate current noise equations are I square Nd is equal to 4 kT gamma G D0 delta F. I square Ng is equal to 4 kT rho Gg into delta F, where Gg is equal to omega square C square Gs by phi G D0, and the correlation coefficient formally defined as C is equal to box of Ing into Ind by square root of I square Ng into I square Nd. Derivation of intrinsic MOSFET two-port noise parameters. The direction of gate noise current is from source to gate and for drain noise from the drain to source. The following assumptions are made. Neglect the thermal noise due to resistive gate material. Neglect CGD to simplify the derivation, and this effect must be taken into account when designing the input matching network. To derive the four equivalent two-port noise parameters, consider the relations Yc is correlation admittance, Rn is equal to En square by 4 kT delta F, Gn is equal to In square by 4 kT into delta F, Yc is equal to Ic by En is equal to Gc plus JBC. So, derivation of intrinsic MOSFET, two-port noise parameters. Further, En and Ind are related by En square is equal to I square Nd by Gm square is equal to 4 kT gamma G D0 delta F by G square M. From above equations, Rn is equal to En square by 4 kT delta F is equal to gamma G D0 by Gm square. The value of an equivalent input current noise is related as I square n1 is equal to I square nd j omega cgs whole square by g square m is equal to 4 kt gamma gd0 delta f into j omega cgs whole square by gm square, that is equal to en square into j omega cgs whole square. Here assume that the input admittance of a MOSFET is purely capacitive and that the input noise current in port 1 is in quadrature and therefore completely correlated with the equivalent input noise voltage. Next, the total equivalent input noise current is the sum of the reflected drain noise current of above equation and the induced gate current noise. The induced gate noise The induced gate noise current itself consists of two terms, one denoted by INGC correlated with the drain current noise, while the other INGU is uncorrelated with the drain current noise. Hence, the correlation admittance as follows that YC is equal to IN1 plus INGC by En is equal to En into j omega CGS by En plus INGC by En is equal to j omega CGS plus Gm by IND into INGC, that is equal to j omega CGS plus Gm into INGC by IND. Next, to express Yc in a more useful form, need to incorporate the gate noise correlation factor. To do so, manipulate the last term in the above equation as follows. Gm into INGC by IND is equal to Gm into power of INGC dot IND complex conjugate by IND into complex conjugate of IND. So here the equation is written as Gm is equal to INGC dot IND by IND whole square, IND square. Gm is equal to ING into IND complex conjugate by I square ND. INGC is equal to cross correlation gate noise current. The last equality The last equality in which ing replaces ings also valid because the uncorrelated portion of the gate noise current necessarily contributes nothing to the cross correlation. The correlation admittance becomes Yc is equal to j omega Cgs plus Gm into ing dot I complex IND by IND square JW CGS plus GM into IND complex conjugate by square root of IN square D into square root of IN square D. That equation multiplied with the whole square root of ing square by ing square d j omega cgs is cgs plus cm gm into ing dot ind by square root of in square g into square root of ind square. J omega cgs plus gm into c into in square g by in square d. Substituting for the term under the radical is Yc is equal to j omega cgs plus gm into c into square root of del omega square by c square gs by 5 gamma g square d0 is equal to j omega cgs plus gm by GD naught into C into delta by 5 gamma omega into CGS. If we assume that C to be purely imaginary, even in the short channel, finally an useful correlation admittance is YC is equal to J omega CGS minus J omega CGS into GM by GD naught into mod C of square root of del by 5 gamma is equal to J omega CG plus 1 minus alpha of C square root of del by 5 gamma. Alpha is equal to Gm by Gd naught. Alpha is equal to 1 for long channel devices. Alpha is proportional to 1 for channel length decreases. From above equation Yc is purely imaginary, so comparing with Yc is equal to Gc plus Jbc comma Gc is equal to 0. Using the definition of the correlation coefficient, we may express the induced gate noise as in square G is equal to INGC plus INGV whole square is equal to 4 kT delta F into delta F del GG mod C square plus 4 kT delta F into del GG minus of 1 minus C square. In the above equation, loss term is uncorrelated portion of the gate noise. G is equal to I naught square by 4 kT delta F is equal to 4 kT delta F Gg into 1 minus C square by 4 kT delta F del omega square Cgs square 1 minus mod of C square by 5 GD0. Source impedance that minimizes the noise figure is BOPT is equal to minus BC is equal to minus omega CGS of 1 minus alpha C into gamma by 5 gamma delta by 5 gamma. Optimum source admittance is G opt is equal to square root of G square root of GO by Rn plus Gc square is equal to alpha omega CGS into del by 5 gamma of 1 minus mod of C square. The minimum noise figure is F minimum is equal to 1 plus 2 Rn G opt plus Gc is approximately equal to 1 plus 2 by square root of 5 omega by omega t of gamma del 1 minus mod of C square. Generalizing the MOSFET noise parameters or parameter expression. So GC value, the expression should be approximately 0. PC WCGS of 1 minus alpha C square root of del by 5 gamma Rn is equal to gamma GT0 by Gm square is equal to propagation constant by alpha into 1 by G. Gu is equal to del omega square minus Cgs square of 1 minus mod of C square by 5 GD0.